Andy, thanks so much for coming on the show. It's a real pleasure having you on. I've enjoyed the times we've got a chance to talk over the years, and I can't think of a better person to talk about how you choose the right technology for the right job, specifically between ultra wideband and Bluetooth angle of arrival. Although for people that want to stay for the second half of the show, they'll hear some really interesting stories about how you've got into infrared and ultra wideband, which is another set of choices. So maybe we'll get onto that later. But first of all, welcome and thanks for coming on.
Thanks for having me.
What is that interesting array of objects just over your right shoulder?
Good stuff, yeah. So this is, we do Ubisense. We make location-aware systems for industrial customers, and about 5% of the world's cars are built using our technology now, and we sell ultra-wideband systems. We sell third-party location systems, including BLE. AOA systems from other people to these manufacturers, and then systems work in terms of software and installation and management that goes with it. And as part of that, particularly for these customers, you have to make sure that it keeps working. They have extremely high reliability requirements. They have, you're allowed basically zero downtime, and it's got to be the right answer every single time. And so a lot of big systems engineering has to go into making that work. So this here is part of our large scale sensor test rigs, where basically we have about, how many is it going to be? 50, 60, something like that, sensors behind there, all working in concert with a cloud server and so on, simulating some of the kind of traffic and traffic patterns that we get in large scale industrial systems. So we check it out here before we roll it out to mission critical sites around the world.
So is this part of product development, or is it part of the QA process for every beacon that you ship?
Oh, this is actually more to do with the system software side of things. So of course, when we ship sensors or when we ship beacons, we do have QA processes. Of course we do. This is actually more of the the system control software and application control software. You have to basically simulate large amounts of data, and we do that actually right in the sensors themselves, so that we can simulate all the paths up through the software and to the application layer to make sure it really is going to work as reliably as we think it is. So just something we've learned over the years. You can't take any chances with this, because nature out there is much more cunning than you could ever be in terms of doing it. So the more you can try it in a representative kind of way, the better your system reliability will be.
So for those of you that are listening, which may be a large proportion of it, this is kind of an array of devices that are maybe the size of the palm of your hand, roughly.
Yeah, sort of paperback book size. Yeah.
And so are those ultra wideband beacons?
No, these are actually ultra wideband anchors or sensors. So these are the things that are placed around the environment and that pick up ultra wideband signals from beacons. And then from there, you gather the data from those, calculate positions, but then they go up through further levels of software. So, you take computed XYZ positions, and then those are turned by software into things that businesses really care about. So, nobody actually cares that much about XYZ coordinates. What they care about is business relevant events. So this is in industrial environments anyway. They care about business relevant events like this tool is now working on that car, or this car is now in this process space. Those are things that the software then works out. And then on top of that, you have further layers of software that do things. So, when this tool is next to this car, program it using these particular parameters. And that's something in the manufacturing execution system or the control system for the factory. So, to make all of that work and all of that work reliably, we do an awful lot of testing to check that when we take our software products and deploy it in factories, that the factory is going to keep working, and it has to. If you stop something like a modern car factory, then it's something like €300 a second is the cost of the downtime. So it's absolutely essential when you deploy these systems that they work, and they work first time, and they keep working for years. So,
and how are those things powered and connected?
The anchors, generally they're connected via power over Ethernet. So I think a lot of pretty much all of the location technologies that people use indoors these days, from a XYZ accurate positioning kind of sense, they tend to have a fixed infrastructure. That fixed infrastructure usually has to have power. So it's normally something where you run a power over Ethernet cable to it, and that supplies both the power and the data. And you can't normally do better than one cable running to these things that does both things. But I think in future that might be something that changes when there are new technologies coming out like 5G that allow reliable wireless interconnection of that kind of infrastructure. You won't get rid of that single power cable that's still there. You've got to still provide the power one way or another, but it might be that power comes over a bus network, something like AC mains, or maybe a high voltage DC bus, where it's actually a lot easier and cheaper to put a new spur in than it is to hook up a PoE line back to a switch in a switch cabinet and all that kind of jazz.
It really is easier. I would have thought PoE would be the easiest because it's not a power cable, it's a data cable that just happens to have a bit of power there.
You can't kill anybody with it, right?
Right.
It's funny. I think the issue isn't one so much of physical ease of running it. It's more the cost of maintenance in these factories, in terms of making sure that your switches are appropriately provisioned, and that the switches are protected against everything else in the factory, and so on. So mains is pretty bulletproof, right? You plug it in, and there's not a lot of thinking that you have to do when you add a new spur of mains. Whereas network provisioning and network management and so on are something that actually have a big hidden cost when you go and put those in.
Oh, interesting. Yeah, because I'd always heard that the most expensive thing to do was to pay an electrician to start laying infrastructure. But I guess what you're saying is the data team actually get paid even better than the electricians.
I think that's probably true. Yeah.
Yeah. Oh, so how many of those do you need in a factory to track everything? And what are you typically tracking in a car factory? Presumably cars and bits of cars, but
so I think that the answer to the how many do you need is a little bit of an open-ended question, right? It could be we have factories where there are 4 of these things, or 3 of these things, and there is a factory where there's about 1,500 of them, right? And it depends on the area of the factory and the kind of applications that you're looking at and so on. So a good application example is the control of tools. So one of the things that's really interesting for Ubisense, and I think where we have some experience and expertise, is in using location information to directly control industrial processes. So somebody like BMW or Daimler, their factory these days is completely different from the factory they had 20 years ago. So when Henry Ford came up with his idea of the Model T Ford production line, he had this genius idea with mass production, which is you make the same car every single time. And every time you do something at a particular station on this moving assembly line, so the cars move past you as they're being assembled, and you as a worker do the same thing every time to every car that goes past. And that was transformational in the way that it accelerated the car industry and reduced costs. The problem is that every car on that assembly line has to be the same, because you don't get the opportunity to chop and change between different options and models and variants. And that doesn't sit well with, today's today's mores, which are that I want my car, which is different from everybody else's. And so what people like BMW and Daimler have done is they've made production lines where every single car can be different. So, my car that I want starts being made on the production line, and then the one after it will be completely different. And the one after that will be completely different as well. So we may actually have 4 or 5 different models on a production line, and we may actually have, millions of variants. So each car is different. And that means that when you do something to a car as it passes you on this moving production line as a worker, like use a high-end screwdriver essentially to put the airbag in, for example, you actually have to set up that tool to do the right thing for the car in front of you. Because if you use the wrong torque or you use the wrong number of turns or something like that, then it can basically damage the frame, or maybe the airbag doesn't go in right, and essentially you have a real problem there. So what those customers now do is that they track all of the tools on the assembly line using tracking technology, and they track all of the cars on the assembly lines. It moves down the line, and they use software to essentially look at the location streams coming in. And when a particular tool is being used on a particular car, instantly the control software recognizes that and sets up the tool to do the right thing for that particular car at that particular point on the assembly line. So from the point of view of the worker, they pick up the tool, they use it on a car, and magically it's set up in exactly the right way without them having to do anything. And so essentially that's how a modern high-end car production facility works. And so to do that, you might have, the biggest factories we've got are, maybe 400 or 500 meters square. So, third of a mile on the side, and, may use 1,000 sensors to do that. So it's, they're quite big systems, and they have to keep working all the time. So you can be working one moment on the hood of one car, and then turn around and fraction of a second later, 200 milliseconds later, you could be working on the tailgate of the next car on the assembly line. And in that time, the system has to have tracked the tool, recognized its move from one car to another, reprogrammed it so that it's now doing the right thing, and done that with an error rate which is kind of probably less than 1 part per million is what's permissible these days. So
wow.
It's a very high-end kind of tracking system, and for that we would typically use ultra-wideband location because of the high tracking reliability that's necessary. And the high tracking accuracy that's required in what's quite a challenging environment with a lot of metal and reflections. But obviously that's the right technology, the right sensor for that particular job, and it might be complete overkill for a different kind of location tracking challenge. Or in that case, is not enough. I mean, there are other technologies which are even more accurate than ultra-wideband. So you always have to choose the right thing for the right job.
Thanks for watching this clip from the Mr. Beacon podcast here on YouTube. You can listen to the rest of this episode on iTunes, Spotify, or wherever you get your podcasts. If you enjoyed it, please like and share this video, and be sure to subscribe for more weekly videos. For more information about Wiliot and IoT Pixels, head on over to wiliot.com.